Hello students, welcome to the class. So in the previous class we have discussed about aldehydes and ketones. As we all know, aldehydes and ketones are the carbonyl compounds, yeah, and we have seen the methods of preparations of aldehydes, ketones, the general methods of preparations, or the methods of preparations of aldehydes only, that is Rosenmund's reduction, Stefan's reduction using acid chlorides and cyanides, right? And we have also seen the general methods of preparation of ketones only, that is using acid chlorides, treating it with dialkyl cadmium, or using cyanides, using some other reducing agents, right? Okay. Then we have also seen the preparation from Grignard's reagent. Even we have seen the chemical reactions of aldehydes and ketones. There are many chemical reactions you have already studied in your classes, but here the very important and very typical reactions have been discussed. That is aldol condensation. We know that when an aldehyde has an alpha hydrogen, I hope that point is very clear. Those aldehydes which are having alpha hydrogens can show this aldol condensation. Even there is we cannot always say that only two aldehydes, similar aldehydes have to be involved. If the two similar aldehydes or two similar ketones are involved, we call it as an aldol condensation. If two different aldehydes or two different ketones or a ketone and an aldehyde is involved, then we call it as cross aldol condensation. Even we have seen Canizaro's reaction, wherein there is an aldehyde without alpha hydrogen. Like formaldehyde and benzaldehyde usually show this reaction, and I've told you this reaction is also called as disproportionation reaction, wherein one of the molecule of aldehyde gets oxidized to carboxylic acid, salt of carboxylic acid, and another molecule gets reduced to alcohol. And you know that oxidation of aldehydes gives carboxylic acids. Aldehydes very well undergo oxidation. So even if you use a very mild oxidizing agent also, aldehydes get oxidized to carboxylic acids. And we have seen which are those mild oxidizing agents also. The mild oxidizing agents, what we have seen is the Felling's reagent, the Benedict's reagent, the Skiff's reagent, and the Tollens reagent. A very important test to detect the presence of an aldehyde group, CHO group, are these tests. For Felling's and Benedict's reagents, if aldehyde is present, we get a red precipitate due to formation of cuprous oxide. If for a Skiff's reagent, you will get pink coloration if it is an aldehyde. For Tollens reagent, you will get black precipitate or a silver mirror. Hence, the Tollens test for detection of presence of an aldehyde group is also called as silver mirror test, right? Ketones, on the other hand, they are very restricted for oxidation. They do not undergo oxidation very well because carbonyl group is very sterically hindered by the alkyl groups. Yeah. Therefore, what happens there? Ketones do not undergo oxidation very easily. Still, under very strong oxidizing agents, ketones undergo oxidation giving mixture of acids. And those mixtures of acids will have lesser number of carbon atoms than the corresponding ketone used. Reduction, on the other hand, aldehydes get reduced using any reducing agent. Aldehydes gets reduced to primary alcohols and ketones get reduced to secondary alcohols. Then Canizaro's reaction we have seen. Apart from that, there are some of the reactions which are shown only by ketones. That is one with nitrous acid, which gives oxamino acid ketone, and another one is bimolecular reduction, which will give us pinacol. It is in higher studies also you will study this reaction. It is called pinacol pinacolone rearrangement. For right now you don't have that entire mechanism, but what you can just remember is when two molecules of acetone, that is the first member of ketone, are subjected for reduction in presence of amalgamated magnesium and benzene solution. The solvent what you use is benzene. Using amalgamated magnesium and benzene solvent, you get pinacol. That reaction is called bimolecular reduction. Okay. Even for the tests for acetone, we have seen, yes, different tests we have seen: Iodiferm test, Legal's test. How to distinguish between formaldehyde and acetaldehyde? Look, students, we have discussed this. I am just repeating once again, glancing over it. Formaldehyde is the first member of aldehyde, that is methanol. Acetaldehyde is the second member of aldehyde, that is ethanol. Yes, you have Felling's solution test, you have the odor test, that is smell test. Yes, and iodoform test also. Filling solution, you may say, teacher, both are aldehydes. Of course, both are aldehydes, but with formaldehyde, you will get a very red precipitate with acetaldehyde, whereas with formaldehyde, you will get reddish brown precipitate. Because when acetaldehyde is treated with filling solution, red precipitate is due to formation of cuprous oxide. When formaldehyde is treated with the filling solution, the reddish brown precipitate is due to formation of copper. Okay, so this was what all we had discussed. Apart from this, also, you have studied many reactions of aldehydes and ketones separately. Fine. Now moving to carboxylic acids and their derivatives. So what about our carboxylic acids? Why we are studying them along with aldehydes and ketones? Let us discuss this point. See students, carboxylic acid, in your first year also you have studied, and we already know carboxylic acids are those which contain C double bond O and OH group, or directly we can write it as COOH group. That means it contains a carbonyl group, right? So therefore it comes under carbonyl compounds, wherein the carbonyl carbon is bonded to alcoholic group. So the general form of writing carboxylic acid is complete form is this: C double bonded oxygen single bonded to OH group, which is abbreviated briefly like this, COOH. Yes. So organic compounds which contain COH group, they are termed as carboxylic acids, and this was for the first time termed by Bayer. It was for the first time termed by Bayer. The scientist Bayer gave this term carboxylic acids. Carboxylic group, it is made up of two groups. One is the carbonyl group and another one is the hydroxyl group. Correct? So when carbonyl group and hydroxyl group combine, it will give us the carboxylic group. Okay. Now, based upon the classification, if you look at the classification of carboxylic group, on the basis of the group to which COH group is attached. See, the carbon atom here, it is bonded to double bonded to oxygen, and it is a single bonded to OH group, double bonded to carbonyl oxygen and single bonded to OH group. Based upon that, one bond is empty. You know that valency of carbon is 4. One bond is empty. That one bond could be satisfied. That one bond could be satisfied by hydrogen. It could be satisfied by alkyl group, or it could be satisfied by aryl group. And here are a few of the examples. You can see here, if it is satisfied by hydrogen, we call it as a formic acid. Formic acid is nothing but, it is where the carbonyl carbon is bonded to hydrogen, and it is the first member of carboxylic group, methanoic acid. The second example is R group is substituted by CH3 group, and it is having two carbon atoms. We call it as ethanoic acid. Yes, or it is very commonly called as acetic acid. Even the carbonyl group can be attached to aryl group. Yes, if it is attached to aliphatic ring, we call it as aliphatic carboxylic acids. If it is attached to aryl group, we call it as aromatic carboxylic acids. And one best example is our benzoic acid. On the basis of number of COH groups present in the molecule, we classify carboxylic acids as monocarboxylic acid. As the term suggests, mono stands for one. So there is only one COH group. Dicarboxylic acid, two COH groups. Tricarboxylic acids, three COH groups. Now, what is the general formula? That is the homologous series of carboxylic acids. It is CnH2nO2. CnH2nO2 is the general formula for carboxylic acids. Or you can say it forms the homologous series with CnH2nO2. Yes, CnH2nO2. So here we have CnH2nO2. Right? So CnH2nO2. This is the general molecular formula for carboxylic acid. And it is also the general molecular formula for esters. for esters. Therefore, I can say carboxylic acids and esters form the functional isomers of each other. Here, N is the number of carbon atoms and it starts from 1. So I can write the first member of carboxylic acid being HCOH, which is called methanoic acid, or it is also called formic acid. And you know how formic term came. It was derived from the Greek word formicus, which means ants. Yes, red ants. Formic acid, because whenever an ant stinge, we feel irritation, right? That is due to nothing but formic acid. Okay, fine. So that is the general formula where N starts from 1 and so on. Saturated and unsaturated monocarboxylic acid, students. Mono stands for single COH group. If it is saturated, means all the carbon atoms are double bonded. Unsaturated means they are single bonded. The carbon atoms have double bonds, unsaturated. If there is all the carbon atoms bearing single bond, then it is saturated. Both saturated as well as unsaturated monocarboxylic acids are called fatty acids. Now you may have the question, why a carboxylic acid is having another term. What is the difference between them? If there are only 1 to 10, or you can say 1 to 10 carbon atoms, we call them as carboxylic acids only. But if the number of carbon atoms exceed 11, 12, 13, 14, 15, then they are called as fatty acids. Okay, they are called fatty acids because they are higher acids. And examples you have palmitic acid, stearic acid, oleic acid, citric acid. You have stearic acid for preparation of soaps. We have seen all of them. Yes, and they are obtained by the hydrolysis of fat and oil. Now, in the carboxylic group, hybridization of carbon is sp2 because it is a carbonyl carbon. Quite obvious, it is sp2. Looking at the preparations of carboxylic acids, you can prepare them from alcohols, you can prepare them from aldehydes, as well as you can prepare them from ketones, and the reaction is called oxidation. Look there, primary alcohols, when you subject it for oxidation, they have not completely, you will get corresponding carboxylic acid, quite obvious. But what is the intermediate product obtained there, students? The intermediate product obtained there is, it is nothing but primary alcohol you have taken, you have subjected it for oxidation. So intermediate compound, what will be the intermediate compound? The intermediate compound will be aldehyde. It will be aldehyde. Yes. So primary alcohol undergoes oxidation to give aldehyde, which further undergoes oxidation to give carboxylic acid, and the carboxylic acid will be corresponding, which means how many carbon atoms are present in the alcohol, the same number of carbon atoms will be present in the aldehydes, and the same number of carbon atoms will be present in the ketones. And you already know which are the oxidizing agents used. Acidified KMNO4, alkaline KMNO4, acidified K2Cr2O7. Yes. Similarly, ketones, if you take, ketones are obtained from secondary alcohols. When you subject secondary alcohols for oxidation, we get ketones. Ketones are a bit less reactive for oxidation, and ketones undergo oxidation to give mixture of carboxylic acids containing lesser number of carbon atoms than ketones. If a ketone is there with 4 carbon atoms, you will get carboxylic acids with 2 and 2 carbon atoms. Understanding? It depends upon what type of ketone you are using. Yes, or you may get 3 plus 1 carbon atom. You may get like this. Okay, so this is about oxidation. Fine. So oxidation of primary alcohols gives aldehydes, which on further oxidation gives ketones, right? Carboxylic acids. Oxidation of secondary alcohols gives ketones, which on further oxidation gives carboxylic acids mixtures. Okay, then by hydrolysis of cyanides, when cyanides are undergo hydrolysis in presence of acid, so you can say acidic hydrolysis, you will get carboxylic acids. Hydrolysis of acid derivatives, even acid anhydrides you take, carry out the hydrolysis, you will get carboxylic acids. Carbonation of sodium alkoxide, carbonation, treating it with carbon monoxide. Carbonation of sodium alkoxide gives you carboxylic acid. So we have examples for it. Then alkene, using alkene we can prepare carboxylic acid. The reaction is called Cauch reaction. When alkene is treated with carbon monoxide and hydrolyzed in presence of water, in presence of H3PO4, yes, that is nothing but hydrogenating agent, under 300 to 400 degrees Celsius at a high pressure, you get carboxylic acid. Yes, if you are taking an alkene with two carbon atoms, carbon monoxide has got one carbon, therefore you will get a carboxylic acid with three carbon atoms. That should be known. If you are taking an alkene with four carbon atoms, you have carbon monoxide with one carbon, so you will get a carboxylic acid with five carbon atoms. Fine. Okay. Then Ernst estrus reaction. Acid chlorides when treated with CH3N2, we get first acyl diazomethane, which on hydrolysis gives us carboxylic acid. Make it a slight correction is there. It is not a ketone. We get a carboxylic acid here. We get carboxylic acid here. Yes. So carboxylic acid is prepared. This method is used to ascend the homologous series, to ascend, to descend, to ascend, to increase the homologous series. The method can be used only for synthesis of carboxylic acids having three or more carbon atoms. That means you cannot prepare, by this method, you cannot prepare formic acid and acetic acid. You cannot prepare formic acid and acetic acid, right? Okay. Then, so these are some of the few methods of preparation of aldehydes, carboxylic acids. Chemical properties of carboxylic acids. See, we can explain the chemical properties on various natures. Before going to chemical properties, let me tell you some of the physical properties. In acids of even number of carbon atoms, see, carboxylic acid with even number of carbon atoms, the terminal CH3 and COH groups lie on the opposite sides, right? So, more effective packing of the molecules in the lattice, if you see, acidic strength is directly proportional to minus I effect and inversely proportional to plus I effect. Remember this. Minus I is nothing but negative inductive effect. That means it will be towards the substituent. So as acidic strength increases when it is towards the substituent, or acidic strength decreases when it is away from the substituent. Now, reactions due to alchemical properties, reactions due to alkyl group, students. So reactions due to alkyl group, that is CH3 group. So we have the first reaction, that is halogenation reaction. What do we mean by halogenation? Acids, carboxylic acids having alpha hydrogen give rise to this reaction. The alpha hydrogen atoms are easily replaced by chlorine or bromine atoms, forming halogen derivatives. Now, how to explain this reaction? I'll show you a simple example so that you can relate it to the different examples when we are discussing. Okay, when we are discussing the questions. Fine. You can see here. So let me say I have CH3, CH2, COOH. I'm going to do halogenation, that is chlorination. Okay. So what does here alpha hydrogen is involved? Only the carboxylic acid with alpha hydrogen. So which is alpha position? This is carbonyl group. So this is alpha position. This is beta position. Correct. So what happens here is, so here the hydrogen of alpha carbon gets substituted with Cl. So let me show you the reaction. CH3C. Here we have hydrogen. I'm going to write only alpha hydrogens. COH as it is. Chlorine you are taking. So let me show it like this. So this chlorine combines with hydrogen and eliminates as HCl, and the chlorine gets substituted here. So what do I get? I get CH3, CHCl, COOH. This is said to be halogenation. If you further carry out halogenation, again there is another alpha hydrogen. So that gets substituted. So CH3, C, Cl, Cl, COOH. Yes, we get this compound. Can you give the name for this compound? So numbering 1, 2, 3. So it is 2, 2 dichloro, 3 carbon atoms, propanoic acid. You cannot say propane 1-oic acid because position of COH group is always terminal and its locant is always 1, right? We need not mention it. Fine. Okay. So here this reaction is called halogenation reaction, and it is very well known as HVZ reaction. It is well known as HVZ, which stands for Hell-Volhard-Zelinsky reaction. All the alpha hydrogens get replaced. Hell-Volhard-Zelinsky reaction. Yes. In presence of phosphorus, monohalo derivative is the main product. Suppose you are carrying out the same reaction, CH3, CH2, COOH. Please do remember this, students. If you carry out, suppose I'll take, instead of chlorine, I'll take bromine. Instead, if here I have not used any reagent, but if here I use phosphorus, red phosphorus, then I'll get CH3, one hydrogen gets replaced with Br, COOH. Further reaction will not occur. So I will get monohalo derivative as the major product. So the question what you read is very important, whether they have said in presence of phosphorus or not. If phosphorus isn't mentioned, you can see complete substitution occurs. But if phosphorus, red phosphorus, an allotropic form of phosphorus is mentioned, you will get monohalo derivative. Okay. Benzoic acid and formic acid do not show HVZ reaction. Can you tell me why? Formic acid, HCOH, and benzoic acid, this is benzene ring, COOH, do not show HVZ reaction. They do not show HVZ reaction. They do not show HVZ reaction. The reason is, here you can see this is carbonyl carbon. Is there any carbonyl alpha high carbon atom? No. Formic acid and benzoic acid, these two compounds do not contain alpha hydrogen, alpha carbon atoms. When there are no alpha carbon atom, there will be no alpha hydrogen. When there is no alpha hydrogen, the substitution cannot occur. The substitution cannot occur, right? So alpha hydrogen is a must. Alpha hydrogen is a must for HVZ reaction. It is a must for HVZ reaction. So please make this point very sure. And for HVZ reaction, if you are not using alpha hydrogen, you will get complete substituted product. And if you are using red phosphorus for HVZ reaction, you will get monohalo derivative. You will get monohalo derivative. Is that point clear? HVZ reaction is a very important reaction, so I have made it very clear. Fine. Okay. So here, so next reaction is due to acidic hydrogen. Due to acidic hydrogen. Acidic hydrogen is one wherein we have acidic hydrogen is nothing but the hydrogen which is attached to OH group. So here, see students, you already know that as carboxylic acids contain R C double bond O OH. So this is the general form. This is acidic hydrogen. Because of presence of this acidic hydrogen, that means oxygen being more electronegative. It will pull the electrons towards itself. Therefore, we can abstract this hydrogen very easily. And those which give out H plus very easily are said to be acids, right? Therefore, I call it as acidic hydrogen, replaceable hydrogen. So when acidic hydrogen gets replaced, suppose you are treating with a sodium metal. Yes, what do you get? This hydrogen gets replaced with Na, displacement reaction. So what do we get? Get RCOONA. So COO minus Na plus. This is nothing but salt. It leads to formation of salt, right? So carboxylic acids or benzoic acids, they form salts with metals, metal oxides, metal hydroxides, carbonates, and even it forms with salts with bicarbonates. Any acid, you have studied very easily. Any acid when treated with metals, metal oxides, forms a salt, right? Yes, so it forms salts with metals, metal oxides, hydroxides, bicarbonates, as well as carbonates, and compounds showing basic nature. Any compounds which show basic nature. So here are some of the examples for it. When ethanoic acid, acetic acid, is treated with sodium metal, we get sodium acetate, CH3CONA, and there is liberation, or you can say displacement of hydrogen gas, typical reaction of an acid. When acetic acid reacts with sodium hydroxide, a base, you will get a salt. Acid plus base always gives a salt and water neutralization reaction, right? That is the proof for neutralization reaction. Then when acid reacts with oxide, metal oxides are basic in nature, correct? So metal oxides being basic in nature, when acid reacts with it, you get again, you expect what? You expect salt and water, right? You expect salt and water. Fine. So here, if you observe the first reaction, there, we have reaction of acidic. We have the reaction for acidic carboxylic acid reacting with what you say, the metal. When acids are treated, we know the typical reactions. When acids are treated with the metals, they displace hydrogen gas, right? They displace hydrogen gas. So you can see there is displacement of hydrogen gas and a salt is formed. So this reaction is called displacement reaction. This is called displacement reaction. Then second reaction, you can see when acid is treated with a base, it is forming salt and water. Quite a simple reaction, neutralization reaction, formation of salt and water. Third one, it is with metal oxides. And we know the nature of metal oxides. Metallic oxides are basic in nature. So since acid is reacting with metallic oxides, we expect salt, a neutralization reaction again, and we expect salt and water. Then next reaction is with bicarbonates. Bicarbonates, carbonates, metal oxides are all bases, right? We get again salt. And since it is a carbonate, there is evolution of carbon dioxide gas. So I can call it as a decomposition reaction. I can call it as a decomposition reaction. So this is also neutralization reaction. This is decomposition. Then with a lead carbonate, we get lead acetate. Yes, again carbon dioxide gas is evolved. Ammonium hydroxide, a weak base. It is a weak base, and I'll get a salt. Yes, I'll get a salt. So ammonium acetate salt is formed. And calcium hydroxide, we get calcium acetate. Yes, so these are the reactions of acetic acid with all bases, or you can say basic compounds. Acetic acid with basic compounds. Then reaction with ketene. You can see there, carboxylic acid when reacts with ketene, two terms. Ket, a keto group. Ene, there is a double bond. So when it reacts with a ketene, it forms an acid anhydride. It forms an acid anhydride with the intermolecular elimination of water. Reaction with diazomethane. Carboxylic acids when treated with CH2N double bond N, diazomethane, we get methyl ester. Diazomethane is a powerful methylating agent. It will give a methyl group. So it is by using this method, methyl ester is prepared. Reaction with alkene and alkyne. Carboxylic acids when treated with alkene in presence of BF3, boron trifluoride, we get esters, right? RCOOR dash, correct? These are called esters. Or alkyne, if you see, we get alkene group as well as ketonic group present. Reactions, now the next set of reactions is reactions due to carbonyl group. Yes. And the one reaction what we are going to discuss is again reduction. Remember students, whenever this, I'll give you a simple hint how to remember this. Yeah. Okay. The simple hint what I'm going to give you all is, see students, oxidation and reduction to remember in a better way. Yes, I'll make it easy for you all. Let me say I have alcohol here, whether I'm talking about primary alcohol or a secondary alcohol, I have alcohol. When you subject alcohol to oxidation, I will show it like this. Yes, I'll get either aldehyde or I'll get a ketone, correct? And you know, primary alcohol will give you aldehyde, secondary alcohol will give you ketone. Further oxidation of an aldehyde or a ketone. Of course, we know oxidation of aldehyde is very easy, ketone aldehyde oxidation is difficult, but still, what will we get? We get carboxylic acid. Okay, students. So this is using a mild oxidizing agent. We can go this. But if you are using a very strong oxidizing agent, if you are using a very strong oxidizing agent, if you have alcohols, if you are using strong oxidizing agent, alcohols get directly converted to carboxylic acid. Coming the other way around, if you have a carboxylic group and if you carry out reduction, you will get an aldehyde or a ketone. If you have aldehyde or a ketone and you have carry out a reduction, you will get alcohols, both, any alcohol. If you're giving ketone, you'll get secondary alcohol. If you're having aldehyde, you will get primary alcohol. It depends what type of carbonyl group you have used. But if you are having a strong reducing agent, if you are having a very strong reducing agent and you are taking carboxylic acid, so you are having a strong reducing agent, then you will get directly alcohols. So you can show it here also. RCH2OH gives you an oxidation, RCHO, which on further oxidation gives RCOOH. Yes. Or RCHOH R dash. A secondary alcohol on oxidation gives RC double bond O R dash. Further oxidation, it's a bit difficult. Of course, it is bit difficult, and you will get mixture RCOOH plus RCOOH, HCOH, right? So you get mixture. Coming here, backwards, you have a carboxylic acid, carry out reduction, lithium, aluminium hydride, sodium borohydride, get RCHO. Further reduction, you get RCH2OH. If you are getting a ketone here, C double bond O R dash, further reduction RCHOH R dash. So this is all about oxidation and reduction, which you can remember it completely for aldehydes, starting from alcohols, aldehydes, carboxylic acids, or starting from secondary alcohols, aldehydes, carboxylic acids, right? Okay. So this is all about what we say, the oxidation and reduction. Now moving to the next reaction. So reduction and oxidation we have seen. So it is due to carbonyl group. So reducing agents used, lithium aluminium hydride or sodium borohydride. And if you are using HI and red phosphorus, we get an alkane. Yes, we get an alkane. Now reactions due to OH group. We know OH group is present, and these reactions are called nucleophilic substitution reactions, wherein OH is a nucleophile, it gets replaced with a different nucleophile. So you can see there, first reaction is with phosphorus chloride, PCl3. phosphorus trichloride, or you can use phosphorus pentachloride. Yeah, so phosphorus trichloride, if you are using, you get substituted, OH group gets substituted with Cl, you get acid chloride, no doubt, and there is formation of phosphorus oxychloride, H3PO3, phosphorus acid. If you are using phosphorus pentachloride, you surely get acid chloride plus HCl plus phosphorus oxychloride. With hydrazoic acid, there are many reactions. Nucleophilic substitution, I can say there are many reactions. Yeah, even alcohols, carboxylic groups, when treated with what you say, HCl in presence of zinc chloride, yeah, zinc mixture, grooves process. We come across grooves process. Even when carboxylic acids are treated with what you say, Lucas reagent, grooves process, we have seen when carboxylic acids are treated with thionyl chloride in presence of pyridine, we get substituted acid chloride, and that reaction you can call it as Darson's reaction. Yes, many substitution, nucleophilic substitution reactions are there, wherein OH gets substituted with the other nucleophile. It might be chlorine, it might be bromine, bromide group, anything. Okay. With hydrazoic acid, the reaction is called Smith reaction. Hydrazoic acid is nothing but N3H. When carboxylic acid is treated with hydrazoic acid, that is HN3 or N3H, in presence of acidic medium, we get RC double bond O N3, where this reaction is a modification of Curtis reaction, yes, which further gets converted to RNH2. Carbon dioxide gas gets evolved, along with nitrogen gas is also evolved. So this reaction is a modification of Curtis reaction. Next reaction is with the reaction due to COOH group. The reaction is called decarboxylation reaction. When you can directly take carboxylic acid, or let us take a salt of carboxylic acid, that is sodium acetate. When it is treated with soda lime, soda lime is a mixture of NaOH and CaO, soda and lime, that is caustic soda and lime, that is sodium hydroxide and calcium oxide. So there occurs decarboxylation. Carbon dioxide is evolved in the form of sodium carbonate, and what we get is methane. Yes. So the number of carbon atoms present in salt of carboxylic acid, you will get the alkane with one carbon atom less. So if you are using sodium propanoate, you will get ethane. If you are using sodium ethanoate, then you will get methane. Understanding? Yes. Okay. Then Kolb's electrolytic synthesis. So when sodium or potassium salt of carboxylic acid is subjected for electric arc, is subjected for electrolysis, there occurs, whenever we speak about electrolysis, we have a cathode and anode. Yes. At anode, oxidation takes place, at cathode, reduction takes place. So we have the reaction wherein we get higher alkanes, or you can say we get alkanes containing double the number of carbon atoms. Okay. So Kolb synthesis, it undergoes free radical mechanism. Fine. Okay. Then Hunch decay reaction. When the silver salt of carboxylic acid is treated with halogen, you can take, usually when we say halogen, we always go for either chlorine or bromine, because fluorine is least reactive and iodine becomes highly reactive. So we usually ignore those two. We go for chlorine or bromine. And whenever we are using chlorine or bromine, we maintain the inert solution, inert atmosphere medium, using carbon tetrachloride or carbon disulfide. So here we have taken CCl4. What we get is we get alkyl halides. Carbon dioxide gas is evolved and silver chloride or silver bromide is formed. Okay. So in the reaction, decarboxylative halogenation of the acid takes place. The reaction is useful in stepping down the homologous series. Now, which are the acid derivatives? So the acid derivatives are nothing but if you replace OH of COH group in the carboxylic acid by an atom or another group, it gives acid derivatives. So you can see there I have mentioned some of the acid derivatives. So the acid derivatives are when you replace the OH by X, X is nothing but halogen. What do we get? We get acid chlorides. That is also acid derivative. That means it is derived from an acid by replacing OH group. Then if you replace it by OCOR, we get anhydride. We have seen these reactions. If you replace it by NH2, we get acid amides. If you replace it by OR, that is alkoxy group, then it is ester. These all acid chlorides, you can call it as acyl chlorides also, acyl halides, acid anhydrides, acid amides, and esters are nothing but acid derivatives. Yes, so acyl chloride are most important acid halides. The first member of this family is acetyl chloride, because if you see acetyl chloride is the first member, CH3COCl, and we will be using this frequently. We never say the first member is formyl chloride, HOCl, because it is very unstable. Similarly, acetic anhydride is a representative member of acid anhydrides family. Formic anhydride is unstable. Please do remember. The first two members of acidamide family are formamide and acetamide. So in amides, we have formamide and acetamide. Both exist. Esters have functional group isomerism with the acids. As I have already discussed, their general molecular formula. They form the same homologous series with the general molecular formula CnH2nO2. Therefore, we can call them as functional isomers of each other. Okay. Then moving to the basicity. Order of basic character depends on Z group, where Z can be halogen, it can be NH2 group, it can be OCOR group, or it can be alkoxy group. And here is the order you can see. Acid chlorides, they are more reactive. Then comes acid anhydrides. Then comes acid esters. Then comes acid amides. Yes, derivatives regenerate the parent derivatives on hydrolysis. If you want back the acid, you need to just hydrolyze any of these, you will get back acids. So which one gets hydrolyzed very easily is the order which is being given, rate of hydrolysis, reactivity rate. Most reactive is acid chloride, then comes anhydrides, then comes esters, then comes amides, right? Okay. Then we have some of the important points, like we have some of the important points here to be discussed. Order of reactivity of carbonyl compounds. So see, how do the additions occur? We have seen aldehydes and ketones undergoing. I'm just recapitulating what we have discussed. So aldehydes and ketones, we have seen the reactions like oxidation, reduction. Yes, we have seen all the different named reactions. Yes. So here, if you just carefully listen, oxidation, reactivity of aromatic aldehydes and ketones. The aromatic aldehydes and ketones, they are less reactive than aliphatic. Please note these points. Compared to aromatic, if you compare reactivity of aromatic aldehydes and ketones to aliphatic aldehydes and ketones, aromatic are less reactive. Why? Because due to resonance effect, in aromatic aldehydes, there is resonance effect. Aryl group tends to decrease the extent of positive charge. So this makes aromatic aldehydes less reactive than aliphatic aldehydes and ketones. So if you look at the order of reactivity, if you look at the order, even in aromatic aldehydes and all, if you look at the order of reactivity, I can say here, I can very well say, because these are frequently asked questions. So I can say here, benzaldehyde is more reactive than acetophenone, which is more reactive than benzophenone. I need not explain you the structures. I hope the structures are quite clear. Benzaldehyde. I'm sorry, benzaldehyde, CHO, more reactive than acetophenone, the first aromatic ketone, C double bond O, CH3, which is more reactive than benzophenone, right? C double bond O, then here we have this. So it is more reactive than benzophenone, right? Okay, then oxidation, aldehydes, we have discussed it many times, so I need not waste time in telling the same thing. Carbonyl carbon, carbonyl oxygen, yes. Relative reactivity of aliphatic aldehydes and ketones. Greater the positive charge on the carbonyl carbon, higher is its reactivity. As the positive charge on carbonyl carbon increases, the reactivity increases. If you see the steric hindrance, carbonyl compound having smaller alkyl group or lesser number of alkyl groups on its carbonyl group is more reactive due to less steric hindrance. So if I want to ask you, like for example, CH3, CHO and CH3, CH2, CHO, which is more reactive? This is more reactive because there is a small CH3 group and here there is a big CH3, CH2 group. So what factor comes here? The factor of steric hindrance appears. So lesser number of carbon atoms makes it more reactive. And in general, ketones are less reactive than aldehydes. In general, ketones are less reactive than aldehydes because you already know the reason. Yeah, ketones you have R, C double bond O, R dash, and aldehydes it is R, C double bond O and H. So H is a small group and here there is a bulkier R and R dash group. Here there is one R group and one H group, H hydrogen atom. So due to less steric hindrance on aldehydes, aldehydes become more reactive, whereas ketones become less reactive. Okay. Haloform reaction, when treated with iodine and sodium, you get with iodine in presence of an alkali, these compounds which have methyl ketones, they get iodized to CH3I. Yellow color is obtained, right? So that is called iodoform reaction. It is a typical reaction which is shown only by methyl ketones, right? Methyl ketones. Then we have seen in carboxylic acids, acidic strength. Carboxylic acids are weak acids, stronger acids than phenol and alcohols. If you compare the acidic strength of carboxylic acids, they are weak acids. So carboxylic acids are weak acids. But when you compare with phenols and alcohols, phenols, you have less acidic than alcohols. They are less acidic than carboxylic acids. So they become more acidic. Trichloroethanoic acid, if you see, for example, see, as the number of electron withdrawing groups increase, COH is a stronger acid than dichloro, Cl, CH, Cl. That means as the number of electron withdrawing groups increase, the acidic strength increases. Okay, fine. Greater the electron withdrawing tendency of a substituent, stronger is the acid. So rather than saying see, fluorine, if you have fluorine, that is more acidic, chlorine, bromine, and iodine. And as the number increases, if there are 3 chlorine atoms, that becomes more acidic than 2 chlorine atoms, than 1 chlorine atom, than no chlorine atom, no chlorine atom, right? No chlorine atom. Okay, fine. As the distance of the electron withdrawing substituent from COH group increases, acidic strength decreases. So let me see here, CH3, CH, Cl, COOH, yes, and here I have CH2, Cl, CH2, COOH. Number of carbon atoms are same, but the distance from COH group, this is electron withdrawing group. The distance of electron withdrawing group from COH is far. Acidic strength decreases. Here it is near. Electron withdrawing group is near. So acidic strength increases. Acidic strength increases. Yes. Now, effect of substituent. Yeah, effect of substituent. If you want to see the electron releasing groups on benzoic acid, if you see the electron releasing groups decrease the acidic strength, the electron withdrawing groups increase the acidic strength. If benzoic acid is having electron releasing group, it will decrease the acidic strength. If it is having electron withdrawing group, it will increase the acidic strength. Whereas orthoisomer is strongest of all isomers because of ortho effect. Yes. Then we have seen the different reactions. Reduction we have seen. Carboxylic acids under different conditions give different products and as reduction products. So if you take lithium aluminum hydride, it will give alcohol. Instead of that, if you take HI, hydrogen iodide and phosphorus, it gives alkene. Substitution reactions we have seen. Benzoic acid. Benzoic acid undergoes halogenation. Yeah. And we get ortho and para substituted product because COH group, we get ortho and para substituted product or meta product. That depends on COH group. COH group is an electron withdrawing group. It decreases the electron density at ortho and para position. Therefore, meta position becomes available. So we get for substitution, for electrophilic substitution of benzoic acid, aromatic carboxylic acid, or you can take for aldehyde, aromatic aldehyde, that is benzaldehyde, or you can take ketone, that is acetophenone. We will get meta substituted product. Yeah, we get meta substituted product. However, COH group, that aromatic carboxylic acids do not undergo Friedel-Crafts reaction. Okay. Aldehydes, ketones, and carboxylic acids are highly polar molecules. They are prepared by dehydrogenation, controlled reactions. So we have seen entirely all the reactions. Yes, we have seen all the reactions of carboxylic acids, the methods of preparations of carboxylic acids. All the methods are being seen. So we have seen what are derivatives of carboxylic acids. Yeah. So this is all about the synopsis, a brief synopsis on aldehydes, ketones, and carboxylic acids. Based on all these synopses, we'll be discussing the questions on the aldehydes, ketones, and carboxylic acids. Thank you.